Chapter 21, Chemical Reactions. What is a chemical reaction? It is a change in which one or more substances are converted into new substances. What then is a substance? It is an element or compound. See where in the picture you have two hydrogen gas molecules about to combine with one covalently bonded oxygen molecule? Just as there are two sides to every argument, like mine and of course the incorrect one, there are two sides to every chemical reaction. Remember what a chemical reaction is? It's when electrons are shared, given, or taken between compounds. So it's the electrons. Chemistry has come a long way since its early origins, attempting to turn lead into gold. And part of that was to develop an effective way to communicate knowledge. In a chemical reaction, we have a name for the elements that go into a reaction and a different name for the chemicals that result from a reaction. The substances that react are called reactants. This makes sense. The reactants are the substances that react, the before elements. The compound that is produced from a chemical reaction is called the product. The products are the substances that are produced from the reaction, the after. Remember conservation of mass? Look closely at the name. What do you think it might be? It means in a closed system, the mass of the products must equal the mass of the reactants. Pause a minute and think about what this means. In a closed system, the mass of the products must always equal the mass of the reactants. In this example, we are breaking down mercury oxide into its two components, oxygen and mercury. How much oxygen will we get? This is one of the experiments that the founder of modern chemistry performed. He would heat mercury oxide until the bonds broke. He would then collect the oxygen and breathe it in, sharing it with his colleagues. While I wouldn't recommend it due to the toxic effect of mercury, he did not suffer from mercury poisoning because he breathed in only the oxygen, though he did meet with an untimely end. This conservation of mass sounds like such a simple principle. Chemists always discounted the effects of gas, especially burning. They did not understand what gas was. Carbon literally goes up in smoke, but they didn't realize that. Smoke was not considered to be made of elements, hence carbon found in wood was assumed to just magically disappear when it burned. Today we know that it is being combined with oxygen to create a gas that is lighter than air. It was incredibly important to put a lid on it and capture that runaway gas. The first person to do so was Antoine Lavoisier. He was the first to experiment with a closed system. Before that, gases were lost to the atmosphere, such as when leaves are burned in the fall. Lavoisier proved that although matter may change its form or shape, its mass, that's the amount of there is, always remains the same. If you measure the carbon in wood and measure the carbon in the carbon dioxide produced when you burn wood, you will get exactly the same number of carbon atoms. It's not magic, it's chemistry. Antoine Lavoisier was a French nobleman born in 1743. He's considered the father of modern chemistry. While he did not discover oxygen and hydrogen, he was able to recognize that they were separate elements and gave them their names. Lavoisier put together the first extensive list of the elements, which was used by Dmitri Mendeleev when he created the periodic table about 100 years later. Lavoisier also reformed chemical nomenclature as well. Nomenclature, remember that? That is naming. That's how ionic and covalent compounds are named. We just completed that chapter. Before Lavoisier, it was much worse. He also helped construct the metric system. Unfortunately, his ending was very unfortunate. For helping develop the metric system, he became part of the enemy and was one of the many people who lost their head in the French Revolution. A chemical equation is a formal method for describing the chemical reaction using letters, numbers, symbols, and coefficients. It is how we communicate what is happening in that little beaker. You have reactants on the left, a yield symbol. Let me show you that yield symbol. That's the yield symbol. Showing the chemical reaction, that's the swapping of electrons, don't forget, and the products on the right. Often, it is also important to show what state the reactants and products are in, such as solid, liquid, or gas. A special category for solids dissolved in water, in liquids, water, is called aqueous. Think of sweet tea. The sugar is dissolved in water. Liquid sugar would be if you melted the sugar on the stove directly without adding water, such as when you make peanut brittle. Notice how much more brief the chemical equation is over the description. You can also manipulate the chemical equation using mathematical techniques. If you are into that, please take advanced chemistry courses. Yay! We won't be covering advanced manipulation of chemical equations in this course. That's too bad. Coefficients represent the number of units of each substance that take part in the reaction. A unit is, notice the oxygen, comes in a set of 2. Up until this point, we have always put the number as a subscript, where the 2 means oxygen has bonded with oxygen, and there's 2 atoms. It is really oxygen gas at this point, but we still call it oxygen, the same as the single element, which leaves room for confusion. What if we need more than one oxygen gas molecule in our reaction? That's where the coefficients come in. We use coefficients to show how many oxygen gas molecules, O2, we need to create the product. In this case, we need 4 aluminum combined with 3 oxygen to create 2 aluminum oxide. Think of coefficients as how many packages of bread, cheese, or bananas will you need to make sandwiches. You can't buy just one slice of bread. It only comes in a loaf package. Cheese is generally purchased by the pound. Bananas, however, can be purchased individually. Compounds are the same way. You use coefficients to show you want 1 loaf of bread, but bananas, since they can be bought individually, you can put a 4 in front of it to show you need 4 bananas to make enough sandwiches for the crowd coming over to watch NC State beat UNC. Yay! Because mass must be conserved, coefficients are used to balance an equation. Balancing means that the same number of atoms of each element must be on both sides of the equation. Count the number of blue aluminum atoms. Notice how they are the same on each side. This means that the aluminum atoms, at least, are balanced. You are not pulling aluminum atoms out of thin air for this reaction. Pause if you need to take a look at it. Can you pull atoms out of thin air? Well, maybe a couple of oxygen atoms or nitrogen atoms, but not much else, and certainly not aluminum. Since Lavoisier put a lid on it, we know about conservation of mass. You can't just create atoms just because you need them. You must get them from some source. Chemical equations describe the change of reactions to products and obey the law of conservation of mass. Now it's your turn. Are you going to tell her no? I would not tell her no. Let's work this one out step by step. And then you're going to work the ones out by yourself. There's lots of ways to do this. The way I like to is I'm going to put that I need to do oxygen over here, and then below it I also need to balance aluminum. And remember that arrow means yield. How many do I have over here oxygens? Well, I have one set of 2, so I have 2. So let's just write a 2 here. Okay, on this side I've got 3, so that doesn't look too good. Well, that's not balanced. I might as well not go any further because I can't balance that. So I come over here. What can I do? I need more. Well, how am I going to make 2 into 3? Well, I can multiply this by 2. Okay, that gives me 6 over here. Well, I have 6 over here. How do I get 6 over here? I have to make this 3 now. So 3 times 2, this is now 6. I have 3 packages, there's 2 in each one. Okay, so that's balanced. Now let's look at aluminum. Aluminum over here has 1. Let's see on this side. Aluminum has, there's 2 packages of 2 each, so there's 4. So I'm going to write 4 here. And that's how many resulted. How do I pull that out of thin air? Well, I can't pull it out of thin air. So I have to go over to my reactant side and say, how do I make this look like 4? I have to say, when I order the cheese, or in this case aluminum, I'm going to say I want 4. And then I write that down here, 4. So that's balanced. I have 6 oxygen, both before and after, 4 aluminum, both before and after. I'm a balanced kind of person. Now I want you to try this one. Pause if you need to. First step, I'm going to write nitrogen. Next step, I also have hydrogen. Well, it doesn't matter which side I start with, so let's start over here. I've got 2. Okay. Well, I only have 1 in the package there, so I must have 2 packages at least. Okay, so now that's settled up. Okay, let's look at hydrogen. Well, over here I have 2 packages of 3 each, so that's 6. Okay, and this comes in packages of 2. How do I get 6 altogether? Well, I have to make that 3. Okay, so 2 times 3 is 6. Again, think of it as this way. I have 3 and they're packages of 2. So hydrogen comes like there's 2 hydrogen molecules, another 2 hydrogen molecules, and another 2 hydrogen molecules. Whereas over here, it's packaged a nitrogen, and then I have hydrogen. 1, 2, 3. It's the only way I can get it. I can have more though, but they've got to be exactly the same way. 1 nitrogen and 1, 2, 3. I use the squares and circles. They don't really use that. I'm just using that to try and visualize it in my head. You can use whatever works for you. Okay, so that's balanced. Let's go try another one. That's all for this session. Please review the information in Chapter 21 in our textbook. There is so much more that I haven't had time to review with you. It's great stuff. It's the stuff of reactions. Enjoy.